Okay, thank you all for coming. Today we're happy to have Udi Strobach from Volcani Institute. So Udi did all his degrees, bachelor's, master's, and PhD in Ben Gurion University, working on improving short-term forecasts, and then went on to do a postdoc at NASA, in combination with Maryland University on Earth interactions, and after that he came back to Volcani Institute as a researcher, and he's currently working on the effect of climate on climate change, vegetation, and he's going to share results both from his postdoc and current work here.
Good. Good. Okay. So thanks for the invitation and good morning, everyone. So right now I'm working at the Agricultural Research Organization, Machon Volcani, but in this talk I will not talk much or at all about agriculture. This work actually started when I was a postdoc at NASA about 5-6 years ago. There I studied Earth interactions, mostly using the coupled modeling approach. And luckily I was also able to transfer this work to this region, so I'm still working on this project, but the attention was shifted from the global ocean to our own Mediterranean and Israel. So that's the topic of the talk, and this is an outline, so I will spend some time on background and introduction because I assume that most of you are not familiar with this field. So background on LC interactions, and I will also talk about the importance of the small scales, and I will also define what is a small scale for us. And after this background, I would like to go relatively briefly on 3 different studies. One that was initiated back then when I was in the US, local LC interactions in the Gulf Stream. And then another more recent studies, one on the January 2020 flood event that was here in Israel, and a more regional study on the interaction between cyclones and eddies in the Mediterranean. So background on Earth interactions. The oceans provide most of the inertia to the climate system. This is because they have large mass and high heat capacity. And therefore they are very important. They are a key component in regulating climate conditions here globally. There are 3 main exchange properties between the atmosphere and the ocean: water, heat, and momentum. And here I list the subcomponents. So in terms of water, we have runoff and precipitation that add water to the ocean, evaporation that is mostly directed upward. In terms of heat, mostly downward shortwave radiation, emitted longwave radiation, mostly upward, and sensible and latent heat fluxes, turbulent fluxes. And of course, latent heat is directly connected to evaporation. And the wind stress is the momentum flux between the atmosphere and the ocean. And in between these fluxes, there are 2 important state variables, surface winds and sea surface temperature, SST, which directly influence most of these fluxes here in this rectangle. So they are very important variables, and it is already established that the large-scale ocean circulation is driven by these surface winds, and the large-scale atmosphere is influenced by large-scale sea surface temperature variation. However, when we look closely at the ocean, we see that it is organized in relatively small features, and small features I mean relative to the atmosphere. So in the atmosphere we are used to the synoptic scale, so thousands of kilometers. And in the ocean we are talking about more mesoscale, so hundreds of kilometers and even less. So the ocean is organized in these relatively small features. This includes the main streams like the Gulf Stream, the Kuroshio, and the Agulhas, and relatively circular patterns, mesoscale eddies, vortices of rotating currents, and anomaly in temperatures. And also submesoscale features. These are typically very long and thin filaments with a thickness of less than 50 kilometers. So these two fluids, the atmosphere and the ocean, they interact with each other. They both have different time and space scales. So in the end, we get interaction which is relatively complex and very non-linear. And in my studies, we are trying to understand these complex interactions better. So just to illustrate that the difference between these two, between the atmosphere and the ocean in terms of the spatial and temporal scales, so this is a high-resolution simulations that I did a few years ago. What we are looking at here is the fresh water flux. So blue is precipitation, and red is evaporation. But the main characteristics here, if we focus on mid-latitudes, we see patterns at synoptic scale, so thousands of kilometers, and the characteristic time scale is several days, maybe weeks, at least in terms of the distance between two such synoptic systems. So this is just to characterize the atmosphere, and to contrast this with the ocean. Here I'm showing this is the sea surface speed in the ocean, so currents. So we see completely different behavior. What pops up mainly is the big currents, so the Gulf Stream, the Kuroshio, and the Agulhas, and Brazil current, and many circular patterns. That's the ocean eddies. So the spatial scales that is the most prominent here are the mesoscale. The mesoscale in terms of the spatial. In terms of the temporal characteristic scales, we see that everything evolved much slower. So months, weeks, months, and even a longer time step. Okay, so that's just to contrast these two fluids, the atmosphere and the ocean. In terms of their interactions on large scale, when we look on the basin scale Earth interactions, what we see is that surface wind and sea surface temperature, they are negatively correlated. So positive winds, regions with positive winds, like what we see here. So we have here wind zero and sea surface temperature anomaly. Regions with strong winds, we get colder ocean, and regions with weaker winds, the ocean is warmer. So this is illustrated for the Pacific and also for the Atlantics. So negative correlation when we talk about the large scale, the basin scales. However, when we focus on smaller scales, on a mesoscale, we see an opposite behavior. We see positive correlations between sea surface temperature and winds. So this is, for example, a frontal region in the ocean. One side of the front is warm and the other side is cold, and we had a wind blowing across the front. In this case, we typically see stronger winds above the warm side of the front and weaker winds above the cold side of the front. So negative correlation between these two. And this is based on satellite observations, and there are during time, two mechanisms were suggested to explain why we see these positive correlations. We actually expected the negative correlation, right? We have strong winds, this induce latent heat flux and cool the ocean. And here we see the opposite behavior. So two explanations. The first one, we call it the downward momentum mixing mechanism. The idea here is that when the wind is blowing above the front, let's say from the cold to the warm side of the front, above the warm side, the atmosphere will be less stable. This will induce turbulent motion, and then a transfer of momentum from the upper levels into the surface, so we get stronger winds at the surface. And traditionally, we measure it by looking at the correlations between wind stress divergence and downwind SST gradients, and we expect positive correlation between these two properties. And this is what is shown in this specific study for the Agulhas and for the Gulf Stream, and also positive correlations between wind stress curl and crosswind SST gradient. It is more intuitive. If you look here, you will see that weak winds, strong winds, if it blows from the cold to the warm, so here we will get divergence. And if the wind is blowing from the warm to the cold, we will get convergence. And also in terms of the curl, if it's blowing along the front, or if the warm side is to the right or to the left, then we will get positive or negative wind curl and correlation with the SST. So this is one mechanism. So downward momentum mixing, we have momentum, more turbulent motion about the warm side of the front, and downward momentum from the upper level to the surface. And this is one nice example that found that this downward momentum mixing is important. This is in the Southern Ocean. Here it was found that above warm core circular shaped ocean eddies, we will get stronger winds at the surface, more turbulent fluxes, more clouds, and more precipitation, and the opposite above cold core ocean eddies. A second mechanism that was suggested to explain this positive correlation, this is the pressure adjustment. The idea here is that when we have a warm SST, the atmosphere will adjust to this SST, and we will get pressure, the change in the pressure, in the surface pressure, and then convergence or divergence, depending on whether we have a positive or negative SST anomaly. And traditionally, we measure it by looking at correlation between wind convergence or divergence and SST Laplacian. And this is what is shown in this specific paper from 2008. So the idea here is that red regions are same more or less in the two properties, so wind convergence and SST Laplacian, and also sea level pressure Laplacian is also correlated with these two properties. So that's the pressure adjustment mechanism, and this is one example for the pressure adjustment, one nice example of a case where this mechanism is important. So this is over cold wake. So when a tropical cyclone passes over the ocean, it leaves a cold trail behind it. And here they show that above this cold trail, we get something that looks like a secondary circulation. So we have divergence at the surface and convergence at the upper levels. And the explanation is it was found that it's the pressure adjustment mechanism that was acting in this case. So two explanations, and there are also studies that were trying to to investigate what's the relative importance of each one of these mechanisms. So this is a nice idealized study. So it's a composite analysis. We have warm core at the center. So they just put many warm core eddies on top of each other, and they rotate to the right. They rotate them to the right direction of the wind. And so we have two cases. The upper columns is strong background wind conditions and weak background wind conditions. So a strong wind was defined here above 10 meters per second. So these two are wind divergence. And you see that in this case, in the upper row, this one correlates with the downwind SST gradient, so downward momentum mixing is important in this case. And in low wind conditions, the wind divergence correlates with the temperature Laplacian. So for low wind conditions, it's the pressure adjustment that seems to be more important. So far I was talking about local effects, so what happens above the eddies and above warm and cold anomalies, but now we also understand that these relatively small scale features, they may have effect also on the large scale atmospheric conditions. And in this context, I'm showing here, this is the sea surface temperature variability. So that's just month-to-month variability, standard deviation of the monthly SST. And here, this is the latent heat flux variability, also month-to-month variability. And what we can see here is that these two are highly correlated. And this is also what was concluded in this specific paper. The contribution of SST to latent heat variance is over 50% in much of the western boundary currents. And also in other regions, but you see that these are the most variable regions globally. So the high correlation with latent heat, which means that this SST also controls moisture supply to the atmosphere. So it may have effect on the global water cycle. And this is a nice idealized study that actually showed it in a modeling study. So here they used a setup. They ran the WRF model, the atmospheric model. In the first simulation, the control simulation, they just provide the north to south sea surface temperature gradient. So the scales here are, this is more or less mid-latitudes and poles. So they try to imitate the average zonal temperature gradient. And in this case, in the eddy case, so it's the same average zonally, but they also include the effect of eddies. So two simulations, and here I'm showing the pressure and latitude. This is the wind, pressure latitude plot, and this is the wind. So that's supposed to be the tropospheric jet, upper tropospheric jet. And what they see here, when they compare between simulation with eddies and without eddies, is that everything was shifted to the north. So the inclusion of these eddies results in a shift of the eddy, of the tropospheric eddy-driven jet. Another nice example, remote landfall in atmospheric rivers. So that's like real rivers that we have like over the ground, but these are flowing on top of our head. So these are defined as large amount of water that flow in the air column above us. So again, it's a similar idea. Running two simulations, one with eddies and another one that they clean the eddy motion. And what they see here, an increase in this landfall in atmospheric rivers and also a large increase in precipitation. So here they remove the eddies above the Kuroshio, so in the Western Pacific, but the main effect they found over the US, the western part of the US, high increase in precipitation. Another example, European blocking. So this is when cases when the Rossby waves are being blocked by another part of the Rossby wave. So it creates cold conditions, and also here they use two simulations, one with eddies and another one without. And also here they see a shift of the European blocking, a change in European blocking. So when we, in the absence of the SST gradients, they see here a reduced effect of European blocking. Okay, so that was more or less the introduction. So the idea is that we have these small-scale ocean features, and we see that they may have effect on many atmospheric variables above the eddies, and also they may have some remote effects. And in the next part of the talk, I would like to introduce relatively briefly three studies that I did. The first one is the local air-sea interactions at ocean mesoscale and sub-mesoscale in western boundary currents. When I was there in the US, major part of my work was to try to push our model. We used to run the GEOS. GEOS is the atmospheric component of NASA. It's the NASA model, GEOS, and we coupled it with the MIT GCM, which is the ocean model developed at MIT. And we were pushing towards running this specific model at high resolution. So we have two such simulations. Here I would like to focus on the second one, 6 kilometer atmosphere, 4 kilometer ocean, global simulations and coupled. It's a 75-day simulation. These are very expensive simulations, so I used 8,000 CPUs there. They were running for 2 months to generate about 2 months of simulation. But the idea is not to make forecast, of course. Rather, we were trying to understand these air-sea interactions at small scales. And why we want to run these high-resolution simulations? Traditional observations, satellite observations, Quickscat and AMSR for winds and SST. We don't have continuous coverage. We have one snapshot per day, and the resolution is relatively low, 25 kilometers. In our case, we have something which is continuous in space and time, 24 snapshots per day, and a much higher resolution. Also, we have many, many diagnostic fields that we can analyze, not just the surface winds and the SST. We were able to look at many variables in these simulations. So although it's a simulation and still the fidelity of these simulations needs to be tested, right now that's the best tool that we have to study at least remote effect, how these small-scale features affect the large-scale atmospheric circulation. So going back to this figure, as I said, because we have this positive correlation above when the wind is blowing across the front, so the consequence is that we get divergence and convergence depending on the direction of the wind, and also a curl, positive or negative, also here depending on the direction. So in the end, we get this positive correlation between this curl, wind stress curl, and crosswind SST gradient, and wind stress divergence, and downwind SST gradient. And this is one day from the coupled simulation. This is the Goldstream region. And here on the right, I'm focusing on this specific region. This is the SST. So we see that we have very strong SST front in this case. It's about 10 degrees in 20 kilometers in some locations. And here I'm showing the wind stress divergence. So as we expect, we get this. We get negative values. Here the wind is going from warm to cold, so we get convergence. So that's what we expect from theory. However, in our case, the interaction that we see is much more localized than what we expect from previous studies. So we see some kind of a filament rather than a mesoscale feature that we usually used to think about. The numbers that we get, I'm not showing it here, but the numbers are much higher than what we expect. And another thing that we see is that it depends also on the background wind conditions. And this is what I want to illustrate here in the movie. So this is also wind divergence and wind stress divergence and wind stress curl. This one is for the Agulhas, so you can see the SST front in this case. And what I want to show in this movie is that we see these fronts only during specific conditions. This is when the wind is relatively strong. That's the green arrows here. So when we have strong winds that is blowing across the front, we start to see this divergence and convergence patterns. So they are not always there. They are there during specific conditions when the wind is strong. And if we compare it with this specific paper, if I was trying to focus more or less on the same region, we see that here they looked at monthly fields. So they see something that looked like a mesoscale interaction. But when you look on daily fields or hourly in this case, you see that this is actually a sub-mesoscale kind of interaction. It looks like a filament. It has a time scale of several days or even less. And also when we calculate correlations as a function of the background wind conditions, we see what we expect from this movie. So very high correlation when the surface wind speed is strong. This is a correlation between wind stress divergence and downwind SST gradient, and the same for the curl. So high correlation when the wind is strong, but when we go to low wind conditions, we actually start to see negative correlations. Not very high negative, but negative. So positive correlation, but only when the background wind conditions are strong. Another interesting feature that we see in the simulation is that we have a very sharp discontinuity at the location of the front. So that's the SST, this is the front. And we see that during specific conditions, we have strong winds, and then everything becomes red. It's a difference, in some cases, the difference is about 500 watts per square meter. So just when you jump from one side of the front to the other side, you get a very sharp discontinuity, very large difference in terms of turbulent fluxes.
So the SST fronts, are these, so essentially, is this a negative or positive feedback effect? Do the winds intensify the fronts, or do they try to reduce the SST gradient?
In the end, they will. So the wind is relatively. It's changing much. It's much more spatially constant, or it doesn't change much. So in the end, when it blows above something which is discontinuous, it will act to make the difference between the two sides smaller.
Do the winds weaken the fronts, or do they actually intensify the fronts because of the divergence?
No, so in this case they will weaken. You see that they are weakening the front. Yeah, so if you have one side that is cold and warm, and then the wind is blowing, but here you have much higher latent heat flux and sensible heat fluxes, so this will cool faster than this, so the warm side will cool faster. So in the end, we expect, at least this is what I expect, to see that the change in the SST should get smaller. This is a time series, so that's an average over the domain that I just showed. When we look at the 75-day simulation, what we see is that we have 5 specific cases that we get very high latent heat flux. We call it latent heat bursts. 5 specific cases, and here I'm showing the meridional wind, the average meridional wind. And we see that these ones are associated with a strong north-to-south winds, so cold air blowing from the cold side of the front to the warm side of the front. We don't see these latent heat fluxes, these high latent heat fluxes, when the wind is blowing the opposite direction. So positive values, winds blowing from the warm to the cold. We see it only when the wind is blowing from the cold to the warm. And also SST, we see a very significant reduction in sea surface temperature. So in the end, if we connect everything together, what we found in this study is during these specific conditions, when we get like a large synoptic atmospheric system blowing, crossing this front, we get cold air that cross the front from the cold side to the warm side. In these cases, we see secondary circulation, so air from the upper levels goes down. It brings dry air and momentum to the surface. And we see these cases where this is when the latent heat bursts occurred. So here we're trying to explain this in a schematic. So if we have just a cold synoptic front above the ocean without the SST front, we will get upward motion. So the cold and then more dense air will push warm air upward. In case we don't have this synoptic system, but we have the front, we get higher turbulent fluxes above the warm side and higher latent heat. But if we have both of them together, so this cold front crosses the SST front, we get upward motion, but because of this wind divergence at the surface, we also get downward motion, and this downward motion brings dry air and momentum into the surface. So that's what we call a secondary circulation. And also, I showed this before. So what we try to do is to suggest a slightly different paradigm to the more classical one. So the classical one says that above these warm core eddies, we will get more increase in latent heat fluxes because of intensified mixing. What we say is that on top of this feedback of higher latent heat flux, we also get, in some cases, a secondary circulation. And this because of the wind divergence that we have at the front, and this trigger transfer of dry air and momentum into the surface. So in the end, we get a feedback that is stronger by about 30% more than what we expect from the classical paradigm. So this is about this study. So now, when I moved to Israel, I was interested more about to see also the effect of these eddies in our region. So this is one specific study, the impact of Mediterranean mesoscale eddies on precipitation over land. And I think this movie gave me more or less the motivation for this study. So typically the western boundary currents are considered as the most active regions of the world in terms of the SST variability. But when I looked at this movie, this is the vorticity normalized by F. When I looked at this movie, I saw that also here in the Mediterranean, we have a lot of mesoscale activity. So the eddies here are smaller in size, they are less intense than what we see in the large-scale ocean, but still we can see eddy activity everywhere, and many people live around this, the Mediterranean, so even small effects by these eddies may have large implications. At the beginning, I chose one case study, trying to understand what's the role of these eddies in this specific, in one specific system. That's a flash flood that occurred in Israel on January 8, 2020. Here I'm showing the time series of precipitation in two different stations taken from the Israel Meteorological Service. In the northern part of Israel. So most of the rain precipitate on January 8th in both locations. Some rain also on January 9th. The total amount of rain is about 125, 150 millimeters just in 2 days. So that's the specific case I chose to start with. What I did was to run one coupled simulation. The model that I'm using is the Scripps model, which is basically WRF coupled to MIT GCM. This is the domain that I used to run the simulation. It's a 5 kilometer resolution, both in the atmosphere and the ocean. And I ran this simulation for 9 days, between the 1st and the 10th of January. So just to illustrate how the sea surface temperature will normally look like, so very slow evolution, we do not expect much in 9 days, but we do see a positive SST anomaly, kind of an eddy next to Israel and in North Egypt and also in other regions. So that's the SST anomaly. And in terms of the synoptic conditions, so that's 500 millibar height. So we see a low pressure system forms above the Aegean Sea, and then it propagates to the east. In the morning of the 8th, so here more or less this is when we got the peak precipitation in this specific system. And now I let it run again, so, and then it just passed over Israel and goes away. So that's in terms of the synoptic conditions. This is the precipitation. Here we see two phases for the precipitation. The first phase on the 6th, precipitate over, mostly over Turkey. So this part, and then it continues, and in the morning of the 8th, so more or less here, this is when it enters Israel, and in the beginning it precipitates in the north, and then it spreads a day later also to the south. And another interesting diagnostic, I'm trying to stop it. Okay. That's the total column perceptible water, so the total amount of water in a specific column of the atmosphere. So that's the first phase. We see there is a lot of moisture in the air above the Mediterranean, but then it disappears because it precipitates over Turkey. Oops, I need to start it again. So that's the first phase, and then we start to see some mesoscale feature that forms to the east of Crete. So at the beginning it doesn't have a lot of moisture, but then when it propagates, it gets stronger and stronger. And just above these warm eddy regions, it's really intensified and then precipitate over Israel and the eastern Mediterranean, basically. So to study, so that was the coupled simulation, and we were happy with that because we got results that looks more or less like in observation, what we expect from observations. So the next step was to try to see the effect of the eddies. What I did was to run another simulation, SMT, smooth simulation. This simulation is an atmosphere-only simulation. SST was taken from the coupled simulation, so the same SST, but it was updated only once in 6 hours. And another thing I did was to apply low-pass filter on the SST before it is given to the atmospheric part of the model. And to illustrate that, so this is one snapshot of SST in the eastern Mediterranean. So that's before the smoothing filter and after the smoothing filter. So we still get some variability in the smooth case, but we don't have these sharp fronts that we see in a more realistic case. So here, so that's the total precipitation from the last 2 days of this simulation. That's the coupled. And this is the SMT, and this is the difference between these two. So the first thing that we see is that in some locations the differences are really large, so 50 millimeters just in 2 days. So there was some kind of a shift for everything. In the coupled simulation we have more precipitation next to Cyprus. In the atmosphere only, in the smooth, we get more precipitation over Turkey. And also in Israel, we see more precipitation in the south and the north coastal plain, and less precipitation in the central coastal plain. And when I compare it with observations, I also see a similar picture relative to what we see here. So more precipitation in the south and north coastal plain, less precipitation in the center, and also these patterns over Turkey. We see them in the coupled simulation, not exactly in the right location, but you see them here, whereas in the smooth simulation it was completely shifted toward Turkey. So the conclusion here is that the coupled simulation was able to reproduce the precipitation pattern much better than this uncoupled and smooth SST simulation. And also, this is based on the Israel Meteorological Service observations. So also here we can see these high precipitation values in the north and the south coastal plain, and less precipitation in the center. In the smooth simulation, it's just spread all over. So the simulation that I did, the SMT, it's two things together, coupling and resolution, and I wanted also to separate the two effects, the coupling and the resolution. So what I did was to run another atmosphere-only simulation, but in this case I didn't apply the spatial the box filter. So CPL minus ATM, that's basically the effect of coupling, and ATM minus SMT, that's the effect of resolution to first order. And what we see here is that actually the coupled simulation, the coupling was more important, but both of them, both coupling and resolution, contribute to the performance of the CPL simulation in this case. And here it's also an ensemble simulation, so it's not just one simulation here, it's an ensemble of those, and there is also significant line. So we see that the regions that are really red or blue, these are also significant in these simulations. So, yeah, so just to summarize this, this is like a first indication that also here in our region, the small eddies that we get, that we have in the Mediterranean, they also may have large implications, maybe on countries like us. Israel is a small country, and a small shift of the precipitation pattern may have a big difference. And if we can predict them better using coupled simulation, that may help in predicting extreme conditions like that. Another study.
Just need to finish, so maybe
5 minutes.
It's
just 5.
less, yeah.
Yeah, I will do it quickly. Another, very briefly, effect of mesoscale eddies on the intensity of cyclones in the Mediterranean Sea. So in this case, what we are doing, we are using two tracking and identification algorithms. One algorithm to track atmospheric cyclones. So this is for specific cyclones that we had the tracking paths of them in black. And we also identified the location of eddies. And what we are doing, we are trying to see what happened to the storm a day before the cyclone passes over the eddy, and a day after, and also on the day when the cyclone is above the eddies. So, and we choose the most intense eddies because we want to see the effect of the eddies. So the more persistent and intense eddies. And here I'm showing 4 specific cases that we looked at. One specific diagnostic, mean vertically integrated moisture divergence, how much divergence of moisture we had on the day of the storm, on the day when the storm passes over the eddy. In this case, we see quite clear convergence above the eddies. I guess it's hard to see the arrows here, but this region and this region and this region, so we see quite clear convergence of moisture over the eddies. This is in the warm core case, when the cyclone passes over warm core case, and we did it also for cold core cases. In this case, we see a neutral or a slightly negative effect. So divergence, positive values when the wind, when the cyclone passes over a cold core eddy. So just to summarize this part in the end, so we looked at more fields. When the cyclone passes over the eddy, we get an intensified latent and sensible heat fluxes. We also see that the system is intensifying, so a reduction in pressure. Moisture convergence, that's what I showed you, and we also see increase in precipitation relative to the cases when the cyclone passes over a cold core eddy. So yeah, with that I would like to conclude. So I hope I was able to convince you that at least in our, even in our region, these small features may have effect on the local precipitation patterns. And yeah, with that I'm concluding my talk.
Thank you.
So a question about this, I guess, middle part. So when you look at the actual sub-daily time scales of in our region with the flash floods that we have, do you see like individual like cloud bands in the Mediterranean aligned with these eddies? Like in those, if you look at individual snapshots of the SST field and the cloud and the fluxes.
The SST and what? And the fluxes?
Yeah, fluxes, yeah. Did you actually see this alignment occurring on hourly timescales? Where you actually see the large fluxes of...
You mean this specific study or the previous one?
The previous one, yeah.
I was not able to really say that this eddy is what makes this intensification. But what I do see is that the intensification happens above the Mediterranean, and we see less intensification when the eddies are not there, when I smooth the field.
Yeah,
So.
yeah. I guess you say you kind of say individual
Yeah,
eddies.
but it's how to attribute it to one specific eddy.
So in your ocean model simulations so by the way, is this based on an ocean model?
That's the observations, satellite observations.
And then in your other one, I was curious how exactly you initialized your ocean model, and if the eddies that you saw, like we would expect that those are real, like those are these specific eddies that actually happen, or is it just the model is just generating eddies and
Yeah, so that's a short simulation. So basically, that's the initial conditions, what you see. So that's more or less the initial conditions. It was taken from it's a reanalysis product. It's one of the European, I think, SMEM or something like that.
You mentioned
The HICOM. It was HICOM reanalysis. So the initial conditions were taken from the January 1st, 2020. And then I let the model evolve by itself. But so what you see here is more or less quite similar to the initial conditions. So the evolution is relatively slow. So for example, this eddy, it was in the initial conditions that I got.
So your model you're not worried about it needing more spin-up time or
that's why I started it on the first. That's why I started it. So that's why I started it on the 1st of January. But for 9 days, because I wanted to get the initial condition, the signal from the initial condition. So I didn't want too long spin up on one side. I still wanted to keep the predictability that we can get maybe from the initial conditions. But I didn't initialize it on the 7th, right? The precipitation happened on the 8th. But from what I've seen, the spin-up, so if in this specific system, it's the upper ocean that is the most important, and the spin-up is relatively fast. So I was not very much worried about spin-up in this case.
I have a question about this figure, which will maybe say something about my ignorance. How common is this pattern of warm anomalies in the southern part of the eastern Mediterranean versus colder anomalies in the northern part of the eastern Mediterranean?
So when I looked at 20 years, so you can get lower resolution data sets from the last 20 years, you see it moves all over. So sometimes we get negative anomalies and sometimes positive anomalies in this region. So from what I've seen, you get this eddy. This eddy is there for most of the time, but sometimes it's shifted to the north, sometimes to the west a little bit, or to the south. But somewhere you will see these eddy patterns next to us. So it's a question. So for me, it's interesting because maybe it may be important for seasonal predictability and stuff like that.